Today's notes are all about collisions. We've talked about objects colliding before, but we haven't talked about different types of collisions. So in that vein, today's objectives are to list and describe the three types of collisions in terms of whether or not momentum and kinetic energy are conserved, and then be able to calculate the momentum and the kinetic energy before and after any one of those types of collisions. So let's get started. When objects collide, there are three possible outcomes, essentially three types of collisions that they can experience. They can experience what we call a perfectly inelastic collision. They can have just an inelastic collision where it's not perfect, or they can have a perfectly elastic collision. You'll also just hear people call this an elastic collision because there's no such thing as an imperfect elastic collision. Which type of collision depends on two things: whether or not the objects move together after the collision or whether they separate, and whether or not the objects deform and therefore lose kinetic energy, or if they don't deform and kinetic energy is therefore conserved. To begin with, we will discuss perfectly inelastic collisions. If two objects collide and then they stick together so strongly so that they are one mass and they move together afterwards, that's considered a perfectly inelastic collision. So think about, meteor strikes Earth and it becomes embedded in the surface of Earth and continues then to move with the Earth. That would be perfectly inelastic. Two football players, one tackles the other one, and they go flying to the ground together. They're combined their masses together and are moving as one unit towards the ground. That would be perfectly inelastic. In perfectly inelastic collisions, momentum is conserved, and the following equation shows this. This is just a slight rewriting of our original conservation of momentum equation. You'll notice that the left-hand side looks identical to our conservation of momentum equation. The only difference is on the right-hand side, because they are moving as one unit, we're going to combine their masses and they will only have one final velocity because they are now essentially one object. So it's just a rewriting of our original equation. Let's do an example problem with this. Imagine a 1,800 kilogram luxury sedan is stopped at a traffic light, and this little compact car comes up behind it with a mass of 975 kilograms, and it strikes that car, and as a result, they become essentially combined. They get all mangled up together. If the compact car was moving at a velocity of 22.0 meters per second to the north before this collision took place, what would the velocity of both cars tangled together be after it collides? So go ahead and try this one out, and then we'll run it. All right. So let's start by identifying our equation that we're going to use. We're going to use that perfectly inelastic collision equation from the previous page. So that's going to be mass of 1, velocity of 1 initial, plus mass of 2, velocity of 2 initial. And it's going to equal their masses combined times their final velocity. We can identify that we are looking to find velocity final. Okay, so then we're just going to search the rest of this problem for the pieces that we are missing, which would be the mass of object 1. Let's call luxury car object 1. That's mass of 1. And it says it's stopped, which means our velocity of 1 initial is equal to 0. And then here is our mass of 2 and our velocity initial of 2. So now it simply becomes a matter of either plugging these numbers into the equation and solving, or you can attempt to isolate the velocity final, which would just involve dividing both sides by mass of 1 plus mass of 2, right? So if we go ahead and run it then, let's say velocity final of both cars squished together is equal to our mass of 1, which we said was 1,850 kilograms, times our initial velocity, which was 0 meters per second. It was stopped at the traffic light, plus mass of 2, 975 kilograms, times the velocity of 2, which was 22.0 meters per second north, all divided by their masses again combined. And instead of writing north in here, which could get confusing, let's go ahead and just leave it positive, since the general convention is for north to be a positive value. So then when we do the math on this, our velocity final should wind up being approximately 7.59 meters per second, and it's positive, so we would assume they're moving in the same direction to the north. Voila, there's our answer. In an inelastic, perfectly inelastic collision, kinetic energy is not conserved. So in physics, well, I should say, in the general world, we tend to think about elastic objects as objects that are able to deform. In physics, we think about elastic objects a little more specifically. Specifically, elastic objects are objects where the work done on the object to deform it is equal to the internal work done by the object to return the material to its original shape. Inelastic objects, instead of returning to their original shapes, deform permanently because the kinetic energy is converted to other forms of energy. So the objects aren't capable of going back to their original shape, because that energy is essentially lost. We know it's not destroyed, but it's lost to them as it's changed from kinetic energy to some other form of energy, likely thermal or perhaps sound. This decrease in total kinetic energy can be calculated by using that formula for kinetic energy that we have from a previous section. It's important to note, you're not going to lose all of your kinetic energy in these types of collisions, okay? So don't anticipate to lose just this huge portion of it. It depends on how much the objects are deformed, how much energy is lost. Here's our example problem. 2 clay balls collide in a head-on, perfectly inelastic collision. The first ball has a mass of 5.5 kilograms and an initial velocity of 4 meters per second to the right. The second ball has a mass of 0.25 kilograms and an initial velocity of 3 meters per second to the left. What is the decrease in kinetic energy during the collision? Go ahead and try to work this problem using the kinetic energy formula that we have, change in kinetic energy formula, and keep in mind one of your velocities needs to be negative. Okay, so the equation that I was talking about is our change in kinetic energy equation where we have kinetic energy final minus our kinetic energy initial being change in kinetic energy. And then that can be broken down even further where we remember that kinetic energy is 1/2 mass times velocity squared. So we can do that for kinetic energy final and for kinetic energy initial. And then we're also going to have to keep in mind that we have two objects. Okay, so it's going to leave us with some slightly more complex equations. And what I'm going to do is I'm going to break it down into one equation for kinetic energy final and one equation for kinetic energy initial. We'll solve for both of those properties or both of those values, and then we'll plug them back into this equation here to get our final change in kinetic energy, because that's what they want, right? They say decrease, so we're assuming we're losing kinetic energy in this collision, but it's still the change in kinetic energy. Let's go ahead and break down what that would look like. We're going to use for kinetic energy initial, we're going to use the equations 1/2 mass of object 1 times velocity of object 1 initial squared plus 1/2 mass of object 2 times velocity of object 2 initial squared. This is all well and good because we have all of these values, right? We have mass of 1, mass of 2, and we have their initial velocities. The place we're going to get ourselves into a little bit of a pickle is kinetic energy final, because we do not have final velocity, right? So we can write 1/2 mass of 1 velocity final of, velocity of 1 final squared plus 1/2 mass of 2 velocity of 2 final squared. But we don't have that final velocity. So we then need instead to solve for the final velocity, which coincidentally happens to be what we did in our first example problem. So we're going to go ahead and just recycle that equation that we had before to get velocity final, right? Where we said we're using mass of 1, velocity of 1 initial, plus mass of 2, velocity of 2 initial, all divided by mass of 1 plus mass of 2. And we could simplify this equation up here a little bit, since we know it's an elastic collision. An inelastic collision, I have to enunciate, or you miss if I'm saying elastic or inelastic. We could simplify this equation since they are going to combine. We could say 1/2 mass of 1 plus mass of 2 is equal, or not equal, times velocity final squared, because we know they're going to have the same final velocity. So using these three equations, we should be able to solve this problem. Now we just have to plug information in. So when we plug in, let's get our velocity final first. Okay, so this should look like 0.5 kilograms times 4 meters per second plus 0.25 kilograms times negative 3.00 meters per second. I'm going to make that one negative because it's our convention that right is positive and left is negative. And we're going to divide then by 0.500 kilograms plus 0.250 kilograms. And what we should come up with then for our velocity final is 1.67 meters per second, and it's positive, which means these objects are going to move to the right. Okay, so now that we have that value, we'll just keep it over here in our pocket. We'll kind of erase some of what we've got going on here. And we'll solve for our kinetic energies. Man, I wish there was an easier way to erase this. Hey, so now we can plug numbers in to our initial and final kinetic energy equations. So let's just do this one right here because it's straightforward. 1/2 of 0.500 kilograms plus 0.250 kilograms times 1.67 meters per second. And then we're going to square it. When we work that out mathematically, we should wind up with 1.05, and our unit is going to be joules. So this is kinetic energy final. And then we'll erase what we have here and get our kinetic energy initial. So we'll plug in, it'll be 1/2 0.500 kilograms times 4.00 meters per second, and then we've got to square it, plus 1/2 0.250 kilograms times negative 3.00 meters per second, and we gotta square that. And then that should come out to 5, it's a bad drawing, 5.13 joules. That's our kinetic energy initial. So now we can take that original equation, change in kinetic energy is equal to kinetic energy final minus kinetic energy initial. So we can plug in those values, 1.05 joules minus 5.13 joules, which should come out to negative 4.08 joules. That's our change in kinetic energy. And the negative sign indicates that they were indeed correct with the assumption that they made in the practice problem where they said it would be a loss of energy. The negative sign indicates that the energy is lost. The second type of collision we're going to discuss is the other end of the spectrum. These are perfectly elastic collisions. When two objects collide and then those objects separate and they travel in opposite directions and there is no loss of kinetic energy, then that collision is considered perfectly elastic. In perfectly elastic collisions, momentum is still conserved. You're going to see this as a pattern. Okay? So we can still use this equation, but we have to keep the objects separate because they are not going to be sticking together. So we'll have two separate objects moving at two separate velocities after the collision. And in addition to this, unlike with inelastic collisions, kinetic energy is conserved if the collision is perfectly elastic. So we could write this equation where the addition of the initial kinetic energies would be equal to the addition of the final kinetic energies of the two objects. Here's our example problem. A talented juggler can keep as many as 12 identical balls in the air at one time. Suppose each of those has a mass of 0.20 kilograms, and there are 2 balls of the 12 that he's juggling that have an elastic head-on collision during the act. The first ball is going to move away from the collision with a velocity of 3.0 meters per second to the right, and the second ball is going to move away with a velocity of 4.0 meters per second to the left. If the first ball had a velocity of 4.0 meters per second to the left before the collision happened, then what is the velocity of the second ball before the collision? So what we're doing here is we're going to try to identify the initial velocity of ball number 2. Go ahead and give this one a shot, and then we'll run it together. All right, so let's identify some information. Here we have the mass. So lucky for us, the mass, this is mass for object 1 and mass for object 2. They have the same mass. Okay? And then here is our velocity final for object 1. And here is our velocity final for object 2. And then they only gave us velocity initial for object 1. So we have to solve for velocity initial for object 2 using that conservation of momentum equation from before, where we had mass of 1, velocity initial of 1, plus mass of 2, velocity initial of 2, equals mass of 1, velocity final of 1, plus mass of 2, velocity final of 2. Okay, so what we don't have is this little friend right here, velocity initial of object 2. So one nice thing, okay, we could do a bunch of math here, but one nice thing is that because the masses of the balls are the same for all of the balls, then any math we do is going to cause those masses to cancel. So we simply do not need to include them in our equation. So we can nicely just slash out the mass terms and be left with just the velocity terms. What would this look like written out? We would wind up with just velocity of 1 initial plus velocity of 2 initial equal to velocity of 1 final plus velocity of 2 final. And then we can simply subtract this term from both sides in order to get our velocity of 2 initial alone. So this is the equation we're going to use, and at this point, all we have to do is plug in the numbers. So we're going to take velocity to initial is going to be equal to 3.0 meters per second minus 4.0 meters per second. It would be plus, but this is a negative value, so we're going to make it negative. And then we're subtracting another negative value to get our final answer, which is 3.0 meters per second. And it's positive, which means it's to the right. You might have been able to guess that just based on the fact that they had identical masses and it would make sense if one of them swapped their initial for the final velocity that the other one should swap the other way. But there is our answer. Right. We've covered the two ends of the spectrum, but unfortunately, most collisions that we actually run into in everyday life are neither elastic or perfectly inelastic. Okay, they fall somewhere in between. Because very frequently, objects collide, but they don't stick together, which sounds like an elastic collision. But unfortunately, usually when they collide, there is almost always some kinetic energy lost, which is not true for elastic collisions, but it is true for inelastic collisions. So we have a third category of collisions, which would be simply an inelastic collision. It's not perfectly inelastic, but it is inelastic. So in these inelastic collisions, objects collide and then they do separate, so they still move, usually in opposite directions. But there's still a decrease in total kinetic energy during the collision. For the problems that we do in this textbook, we will consider all collisions in which the objects do not stick together to be elastic collisions, because otherwise things get a little messy. So when you come across a problem in the book, even if it doesn't say that it's an elastic collision, if it says that the objects move apart from each other, we're just going to assume that it's an elastic collision. But I just need you to be aware of the fact that for the most part, collisions are not perfectly inelastic and they're not perfectly elastic either. They kind of fall in that middle ground. All right, that is the end of our notes.